So this is lecture number 4. And let us formulate electrodynamics in terms of potentials, V and A. Namely, let's go back to Maxwell's equations and write the Maxwell's equations in terms of A and V, the two potentials. And up here, the Maxwell's equations, the red part refer to the conventional Maxwell's equations. That's what we will talk about in the first part of this lecture. The green terms refer to written in magnetic analogs. And we will make use of the green part also, just for calculational purposes, in the second half of this lecture. All right, so let's just look at the red part of Maxwell's equations. This is divergence of E, this is divergence of B, curve E and curve B. Obviously, let's take a look at this equation. The divergence of B is 0. But we know that the mathematical identity, divergence of curve, is automatically 0. So this equation invites us to write B, the magnetic B, in terms of the curve of the vector potential. All right? Forget about this green part. Look at this equation. Curve E is minus del B by del T. And let's forget about this term for momentarily. Curve of E is 0. That would be solved by E being minus the gradient of a scalar function, which we call the potential. Because curve of gradient is automatically 0. But now there's also this this term, minus del B by del T. And B, we agreed, can be written in terms of curve A. So that means that, E got to be supplemented by another term, minus del A by del T. Del A minus del A by del T, curve A is B. So then minus del by del T, just minus del by del T. So that B and E can be written in terms of the two potentials A and V. And as I said either last time or time before last time, meaning that this part of E refers to the Coulombic part, and this one refers to the part due to Faraday. All right? But A and V are not uniquely determined. Why? Because I can always change A by a gradient without changing the physical field of B. So that if A goes to A plus gradient of a function, let's call it lambda, an arbitrary scalar function. Then the additional part in A would give 0 contribution to B because curve of gradient is automatically 0. So we can always change A by adding in a gradient term. This is known as a gauge transformation. Gauge transformation. But once we do that, change A by this term, then of course that will make a change to the physical field E. That's not allowed. But unless that change is compensated by this term. So that if we make a change in A by this amount gradient taken on a scalar function, then at the same time we have to change V by term minus del lambda by del T. Because whatever additional term in A will be compensated, let's say the sine correct, will be compensated by an additional term coming here in V. So this together form the so-called gauge transformations. And we can always change the two potentials by lambda of this form, arbitrary function, but A at this changed by this, and V changed at the same time by this much. Then the physical fields E and B are not changed. Since this transformation do not change the physical fields A, so we have well, we are free to make such changes. And in particular, we can make changes in A and V in such a manner that we can have an easier time in doing calculations. By that I mean, we are going to choose certain classes of A and V. In particular, we will be talking about two classes, such that the Maxwell's equations in terms of the potentials A and V can be solved easily. One particular gauge, particular choice of the class, particular gauge is well, you know that already. The other one is not well known. Well, probably you do not know that yet. But in fact, there's a more important gauge, a better gauge to choose to do calculations. All right. So now let's write Maxwell's equations in terms of A and V. Obviously, this by choosing B to become A, automatically this equation is satisfied. So it's taken care of. By making writing E in this form and B that form, this equation is satisfied. So forget about this, the green part. For this part of the for this part of the lecture. So when we have two equations remain, this one and that one. We would like to write these two equations in terms of A and V. All right? What's this equation? This equation says divergence of E is that divergence of E. So let me put minus sign minus divergence of gradient would be the Laplacian of V. And then this one minus plus plus del by del T divergence of A. I haven't made a mistake. Minus right. So that would be minus 1 over epsilon naught times the charge density. Okay. And next, what about this one? This one's more complicated. Okay. So let me in fact put a minus sign. Let me put my sign minus. And then, on the right hand side, I have minus mu naught J. And then, this term will be minus the curve of curve A. And then this term, put it to the other side, the left side, will be minus plus epsilon naught mu naught del E by del T. But E is this. So del E by del, I have to write small. That is minus cosine plus y plus epsilon naught mu naught del E by del T. Del E by del T, so this will be minus, okay, minus gradient del V by del T. This is minus, minus, right? Minus del squared by del T squared actually on A. If I'm not made any algebraic mistakes, I found out soon enough. I tend to make algebraic mistakes. And unfortunately, you guys are not allowed to point out my mistakes. All right. Okay, this is the triple cross product. So I can use the vector identities to work it out. So there will be two terms. One term will be induction of gradient. So that will be minus gradient. Both gradient acts on A, so A should be put to the right of both the gradient operators, and then multiply by the grad dot A. That's the first term. The second term will be in direction of A, now minus minus is plus. And then this dot this will be Laplacian. So let me copy. So this. Right. Okay. I haven't missed anything, right? Okay. Minus, so this one, right. So, okay, plus this equal to minus mu naught J. And let me put this term and this term together. Then I have Laplacian minus F naught mu naught del squared by del T squared acted on A. So I'm taking care of this one and the term. Then these two terms would be minus grad divergence of A minus plus gradients we take it out, so plus F naught mu naught del V by del T. I hope I have not made a mistake in sign. Let's see. Okay, this one is what? Yes, this is that. And this term is what's going on the outside. But it looks like I'm correct. Minus mu J. So that the first equation is now like this. And the second, this equation, last equation, is this. So the remaining two Maxwell equations are now in terms of the potentials A and V. And don't forget, we have the freedom to change A and V. And what we're going to choose to do is to take certain classes of A and V to work with. And the first gauge that comes to mind right away is the one that is the class of the gauges such that the divergence of A is 0. So choose the class of gauge of potential such that the divergence of A is 0. This particular choice, particular gauge, is known as the Coulomb gauge. So we are when we use divergence A is 0, we are in fact implicitly using the so-called Coulomb gauge, and you will understand why it's called Coulomb gauge in a moment. Sometimes this is known as also the radiation gauge. Okay, let's see. And this is a gauge we have been using, as I said. Okay, in that case, the first equation is very simple. This complicated term is not there. So that give me Laplacian epsilon V is equal to minus 1 over epsilon naught rho. But this is equation for V that we encounter in electrostatics. And the solution is well known. It's just a Coulomb solution. Hence the name Coulomb gauge. By the way, it says V is function of R and time is equal to 1/4 pi epsilon naught 1 milligram of the charge density of an R prime, and at the same time, over R, which is R with R prime. All right. What about the second equation? The second equation was this n0 would be given by, let me mention that this combination of spatial derivative and time derivative is known as D'Alembert. This is Laplacian, and this combination is called D'Alembert. It's a 4-dimensional operator. Let's say in 3-dimensional case, you use a triangle. So this now refers to one more. This is one more dimension, so making it 4-dimensional. So let's represent this as a 4-dimensional side, a square. And people use this to represent this, but I would prefer to use box square to represent this version. So the box square version, equal A, minus, this term is no longer there, minus, epsilon naught, mu naught gradient, del V by del T, and if I put it to the other side, it becomes plus minus del naught T. So that, now that we know what V is, it's given here, you can substitute V into this term, so that this will depend upon charge density, and then there's the current density there. Then in terms, then you can solve this second order differential equation. So that of the two equations, one is very simple, this one. The second equation is relatively hard. And that's the price you have to pay when we choose the radiation gauge or Coulomb gauge. I myself prefer to choose to work with another gauge. Namely the following. I'm going to choose this combination of A and V to be 0. Divergence of A plus epsilon naught mu naught del V by del T. This gauge, we'll be using this gauge later on in this semester, in the course. This gauge is known as Lorentz gauge. Now, you should have noticed that I spell Lorentz as L-O-R-E-N-Z. There's no T between N and Z. And I confess that I made a mistake when I wrote my lecture notes. I did not know that this gauge is known as Lorentz gauge, named after someone called Lorentz, not the one with the T, the famous Lorentz, of Lorentz transformations in special relativity. And in fact, I found out that there was a common mistake. Most people still think that, in fact, it's Lorentz, there's a T here. Actually, that's not. And to confuse the matter even more, Lorentz with T and Lorentz without T, those two guys, in fact, collaborated. So, but anyway, so it is this. That should be the correct term, the name for the gauge, Lorentz gauge without T. All right? So that right away, this second equation is very simple. This is nothing but D'Alembert. course, now it's understood that both A and J, they are depends upon space R and time t. So the second this equation now is very simple. Then you think, you are going to have to deal with this equation, and I bet you have to pay a price for that. It will be complicated. No. All right. Why? This term in this gauge means that this can be replaced by minus epsilon naught mu naught del V by del T in the Lorentz gauge. So that this term is minus epsilon naught mu naught del squared by del T squared over V. That exactly is the combination. So I have Laplacian minus epsilon naught mu naught del squared by del T squared. So that these two terms combine to be just one term in a way. That's the derivation. Now epsilon on V, and that's equal to minus 1 over mu epsilon naught mu. Notice how similar looking are these two equations. In fact, they are of the same form. So this suffices, in fact, just to solve one or two equations. Then automatically, the other one can be done in the same way. It's just the fact that these two equations are so symmetrical that makes this gauge a nice choice to use. And in particular, this is a nice choice of gauge to do relativity, special relativity. And that also is why people thought that, in fact, this gauge is known as Lorentz with a T gauge, because Lorentz with a T was the famous Dutch physicist who make tremendous contributions to special relativity. Anyway, so this is the Lorentz gauge. All right? And we'll come back to study this pair of equations later on in the course. All right. Now that we have succeeded in formulating the Maxwell equations in terms of the potentials, and the next thing to do is, in fact, to write the Lorentz force law in terms of the potentials. And I think I have no use for this anymore. So I can start erasing this. Let's see. Well, let me leave this here. And I still have to use this. Okay. Lorentz force equation. It's given here. Lorentz force equation. All right. Force acting on touch Q is given Q times E is now given here. Minus gradient acting on V minus del A by del T. That's this term. Then we have this. Plus V cross, and whenever B is given by curl of A. And let's simplify this equation. Well, this is a triple cross product. So there are two terms, one in direction of this vector, the other in direction of this vector. in this direction, and this acts only on A and not on V, but V acting greater than or equal will be 0, since V is not, does not depend upon position explicitly. So in fact, I can put this to the right side of the gradient. All right, so this one can be is gradient V dot A. And another term would be in terms of A minus sign, V dot grid A. And now we notice that we have this term and this term. Let's combine them. And let me, I think we're finished with this. We'll make use of these equations later on in the course. So we are interested in this combination, del A by del T, plus both of them plus V dot grad equal A. And let's notice that we are talking about Lorentz source on a charge Q. So let's draw a trajectory for that charge. Let's say this is the trajectory for that for the motion of the charge Q. And let's say that at this point R, and then time T, the particles here, and then at a slightly later time, so here R plus dr, at slightly later time T plus d time, it is at this location. Let's say that we are interested in finding the difference of the potential A at this point relative to its function, to its value at this point. So we are interested in dA, the total change in A, as you go from this point to that point along the trajectory of the particle. So this is derivative taken at the location of the particle. That will be equal to A at this location, at this time, minus A at this location and at this time. Obviously, for the first term, we should use the expansion. And then with dr and dt being 0, then of course the difference will be 0. But dr and dt equals 0 in that case, then due to the fact that there is time dependence, it depends on time this way, so there will be a term given by dt times del A by del T. And because A also depends upon the location, and if the location changes by that much, so that it will be plus dr dot gradient acting on A. And wait a minute. Oh, okay, yeah. But dr, that much is nothing but V times dt, the instantaneous velocity, times dt. So this one is, may I write this as dt r backward. So that if we divide up both sides by dt, then dA, total change in A, is given by del by del T plus R dot grad acting on A. This kind of derivative, referring to taking derivatives at the location of the particle, is known as covariant derivative. I'm sorry, convective. The one it doesn't sound well. Convective derivative. It's a total derivative. Okay, calculated at the location of the particle. So, lo and behold, okay, so we have del by del T atom A here. Here we have, okay, oh, I'm sorry. Oh, this is V. I said that already. It's hard to think, write, and okay, talk at the same time. This is V. Although some people are very good at doing that. And in fact, okay, I saw quite a few times that Schwinger wrote on the blackboard with both hands at the same time. I don't know how you did it. All right, so this, in fact, gives rise to the convective derivative. So this is equal to, all right, now minus, so that we have this two terms is minus dA by dt. And force, of course, is mass times acceleration. So m v by dt. So take care of this one, that one. Then I'm left with, minus gradient down QV minus gradient V dot A. Let me check. Let me check against my notes to make sure the sign looks a little bit funny, but I could not find a mistake. Oh, in the first place, there's Q. Okay, that's one thing. There's a Q here. And then there's also a Q here, and there's also Q and V. Q and V, yes. How come this Q? What happens? Oh, I'm sorry. Lawrence was wrong. There's Q, V cross B. There's Q. No one has said. So that's Q, Q. So this is Q, this is Q. So have I taken care of all the mistakes? Okay, so this is minus Q minus QV minus, I think it's correct. Now that we have d by dt term, here is what's here. Let's put them together. So let's have d by dt, L V, this goes to the other side, plus Q A. That will be equal to, minus, I can equate it. Minus QV. This combination of mass times velocity and QA has the meaning of momentum. And this combination is known as canonical momentum. Canonical. What property does it have? There's the P denoted by. So this P now stands for this. For this discussion. The ordinary momentum plus QA. So that I can rewrite this equation as d by dt acting on the canonical momentum. Some people put in a subscript canonical at p, so as to remind people that it's the canonical momentum. That's this extra term in expressing momentum that they're talking about. So the rate change of the canonical momentum is given by the gradient acting on V and A. Of course, gradient doesn't act on V when the action on V is 0. So that if V and A are constant of space, independent of position, then of course gradient acting on that would be 0. So constant potentials implied that the canonical momentum is a constant motion. That's the significance of this quantity. Next, let us go back. Let me go back. This is is this. So let me come back. So I'm done with this convective derivative discussion. By the way, this part of the lecture can be found in Griffith's the potential in chapter 10. All right, let me go back to this Lorentz force equation. If I take the dot derivative of both sides with V dot that, on the left-hand side in that case would be d by dt acting on half mv squared. And if I start with v, this term of course will vanish because v dot this term caused this, so this term will be perpendicular to v. So when you dot v will be 0. So the only term to survive will be this. So it's equal to minus q v dot grad. So v dot acting on v, then one side is taken out, plus v dot a. And v does not depend on time explicitly, so I can put this v through this derivative. So plus del by del t v dot a. Oh, I just erased the convective derivative. Remember convective derivative. D by dt is equal to del by del t plus v dot grad. All right. Here, let me make use of this expression for the covariant derivative to rewrite v dot grad here as a difference of these two. So this can be written as d by dt minus del by del t. So that I now have a term d by dt on the right side, which I'm going to move to the left-hand side, since the left-hand side involves a term d by dt. Then I have d by dt acting on 1/2 mv squared, minus becomes plus qv. Is equal to, minus q, minus Q, this terms minus del V by del T. Okay, I'm sorry. What I want is that, in fact, both got Q and both got del T. That's good. Del by del T. Okay. Minus is outside already. Del T. V. And then del. And del this also plus V by A. This combination, okay, is the total energy. So that, okay, E, okay, E by dt is given by minus Q, okay, del V by del T plus V dot del A by del T. So that if the potentials, okay, do not depend on time explicitly, and these two terms are zero, then okay, dE would be a constant motion, and that's to be expected. And okay, you can write okay, the energy in terms of V, okay, velocity, and the potential, okay, or you can write in terms of okay, the canonical momentum. After all, canonical momentum is this. Let me see. Do I want to do that here? Let me check to make sure that I have not made a mistake here. Right. Okay, yes. And E can be written in another form, instead of given by QV plus this term involving velocity. But instead of this, I can put in terms of the canonical momentum. As V is here, so it's given by plus P minus QA squared divided by 1/2 divided by momentum. That's it. All right. So much for the discussion of potential formulations of Lorentz force law and the equations for energy and canonical momentum put in terms of the potentials explicitly. So this is chapter 10. We will not be doing too much of chapter chapter 10, but occasionally we will get, well, we'll see how much time. We do not have that much time, so, and we will not be doing too much of chapter 10, as I said. So this is part of chapter 10. Now we change gear, to go to Griffith's chapter 8. That has to do with conservation laws. And I don't think I will have a chance to use these equations today. So let me erase all of this. Conservation laws, which is a very important topic. Conservation laws for electrodynamics. we would like to find how conservation laws, conservation of energy, conservation of linear momentum, conservation of angular momentum look like for inertial dynamics for a system consistent of both its magnetic field and the charged particles. And as you see, for this discussion, I will be making use of the generalized Maxwell's equations, including the green terms in Maxwell's equations, and just for calculational purposes. At the end of calculation, I will put all those things in zero. Namely, I will put rho m is 0 and Jm equals 0. Okay? Then I'll be talking about the regular Maxwell's equations. Okay? But I want to keep the green terms, the magnetic analog terms there, so as to make the calculation simple and obviously straightforward. Okay? Otherwise, you will have to be smart enough to do some tricks in the process of doing the calculations. You have to put in some terms which are equal 0 in particular ways. Although once you know that, once you heard of the symmetry, the duality symmetry, then you know how to put in terms that are identically 0. But you have to be smart enough to do that. All right, let's start with conservation of energy. For a system, consisting of a particle and a field E and B. So for a particle, Q, in the presence of E and E. Okay. Then the Lorentz force law says that it's Q E plus V plus E. However, I'm going to suppress the subscript E, Q sub E, since Q refers to the electric part, not the magnetic part. So this electric charge. I will add in a term Qm B minus epsilon naught mu naught V cross B. And at the end of the calculation, I will put Qm equals 0. So in fact, this is what I'm doing. Consider the regular conventional Maxwell's equations. But I'm going to put in this term so as to make the calculation straightforward. It's a calculational trick, nothing to do with physics in a way. All right? So let's start with this force law. Force acting on this particle, Q and Qm, carrying both charge Q and another charge Qm. Let's consider this force act on the particle, move the particle by dl. That will give you some work to be done. And if I divide by dt, then this would represent the rate of work done by the electromagnetic field on the particle. Rate of work done on charge particle, on particle. Okay. So this is F dot V. Ha! It's dot V. So that the complicated terms, this and that, would automatically not be there. Oh, good. So this is equal to Q E V dot E plus Qm V dot E. This is for one particle. And now let me talk about a bunch of particles. In fact, let me go into the continuum description. So the rate of work done on the particles inside a certain volume will be given by the volume of this. Okay. Q, okay, oh, this will be changed into rho. Okay. Part V would be J. So J dot E. And this would be Qm, and this would go into, J sub M. Dot B. All right? So, if I put Qm being 0, then Jm will be 0 too. Then it's not there, then that's the quantity that I want to calculate. But I want to put in this side, put in this term, for the time being, and then eventually, I'll put that in 0. Get rid of it, in a way. All right? Now, let me take a look at Maxwell's equations. The term involving J is here. The involving J sub M is here. So let me make use of these two equations to get rid of J, M and J in terms of the fields E and B. This is equal to 1, 2. Oh, let me in fact just say, let me just talk about what's inside the inequality. Let me see how far I can go. Oh, okay. So the integrand. So the rate of work done on the system of particles is given by the volume of this. So this has the meaning of the root density, root per unit volume done on the system. And that is equal to, as I said, so this is J dot E. So J dot E. So let me divide out by mu for simplicity. And then on the minus side. And here, I will have divided out by mu naught. So mu should be in J dot E, just here. So it's E dot, yes, curl of 1 over mu naught E minus epsilon naught del E by del T. Okay? That is this term, and this term, it should be 0. Let me see. I'm going to get rid of it by writing dm in terms of these two terms. So the plus b dot dm is, goes to the other side, is curl of term comes from this. Okay, we put it there, and some people say, I disagree, that term shouldn't be there. Well, let's see, this term is that term. And, look at this. When you put JM is 0, this minus that is 0. So this minus that is 0. So that this is identically 0. So if you did not put this term in to start with, you will not have this term. But still, you will say, I'm going to put a 0 here. Okay, put 0 in this form. This is 0 because of this. Okay. Without the current term there, it's nothing but Faraday's law. But by making use of the duality symmetry, I put in this term, okay, and then I know exactly what I should put in there, so as to make that term there to be obvious. Otherwise, you will say that, I want to put in this term here, which is 0, okay, because of Faraday's law, but which also combined with this is nothing but the duality transformation of this term. You can check this true. Yeah, you can argue that way. But why not, in fact, include this term, so that it's still automatically? That's what I mean by, just for calculational purposes. Let's put in there, and then say the Jm is 0, so it's not there. Okay, I can now put Jm equals 0. Well, nowhere to be seen, so it's fine. And when Jm is 0, this is nothing but 0. So that if D for the case Jm is not there, put in the 0 here, in a very smart way, but not too many people are smart enough to know what kind of zeros to put in. Why not twice 0, for example? Well, of course, it cannot be, because you want this and this to have some kind of symmetry, namely related by duality symmetry. And to continue, let me check my calculations, make sure that I have not made any mistakes. Forget any term. Okay, that E is mu naught. Could be, this term, minus, and then E. That's a minus sign. I've forgotten about minus sign. So that's what I worry about. There should be a minus sign here. There should be a minus sign here. There should be a minus sign. Oh, this JL is, there's a minus sign. So in fact, that's minus, yes. So this is minus. There's a minus sign. And this one I put it right because, I said it. Why is it right? Let me see. Why is there a minus sign? This G is, that's a minus sign, correct. I made a mistake here, minus sign. Well, in fact, I mean, eventually, I do not have to look at the notes. Then, because after the calculation, I will find that if there must be some mistake. All right, and what's this? Okay, let's take care of the time derivative terms first. This and that. Of course, this start with that. Okay, so this is nothing but minus del by del t of 1/2 of epsilon naught e squared, isn't that right? My sign here. Then I have del by del t, there are 2 of them. But then compensate for this one of 2. So this can think of. And this one is never, is plus 1/0. So this, so let me put a 1/2 outside. Mu naught E squared 1/2. That's it. this, and then I have these two terms will be minus, okay, there's the mu naught term, mu naught, and well, then these two terms can combine E dot curve B and B dot curve E with a minus sign, so that should be minus, okay, let me see, so that, right, so that is, okay, dot, okay, E cross B over mu naught, and this would be, okay, this term would be sum of these two terms. So that the rate of work done, okay, per unit volume by the field is given by this. And let me also write, okay, dW by dt, let me write this as volume integral of del, okay, U mechanical by del T. This is nothing but the volume integral of the rate of increase of the mechanical energy of the system per unit volume. So that I would have, okay, in that case, look at the integram, then I have del U mechanical by del T is equal to this. This minus del by del T, and let me call this combination, okay, to be U sub EB, the electromagnetic, to the energy density of the electromagnetic field. And I think briefly, okay, let's use, okay, U to represent this. But let me use, okay, the notation that I'm using in my lecture notes. U, EB, minus, okay, this combination, okay, it has to do with that with gradient, so it represents some kind of flow, okay, in fact, it's energy flow density, and this, okay, by convention is, okay, denoted by S. So S, okay, is, okay, given by, okay, E equals B divided by mu naught, and this, okay, S, as I said, has the meaning of, okay, energy flux, and this has to do with the rate change of the energy density of the electromagnetic field. Okay, so minus divergence of S, and this S is also known as Poynting vector. Poynting vector. Okay, yes, the meaning of energy flux, something to do with, okay, motion, movement of energy. So that, okay, you have this. If I put, okay, all this on one side, it becomes plus. This equals 0. And in particular, okay, if you put in, okay, the volume integral, then it will be, okay, then of course the first one is nothing but dW by dt. Oops. Plus volume integral of, okay, del U B by del T plus volume integral of divergence, of course, okay, that is nothing but area integral of that, 0. So this represents the, okay, change in the energy of the electromagnetic field inside the volume, and this represents, okay, the energy, okay, flow, okay, through the surface, the rate of energy flow through the surface, and then add up with the, okay, change in gain of energy for the system, okay, all add up to be 0. So this is conservation law. And if, okay, dW dt is 0, okay, then you would have, that means that del U mechanical energy is 0, then you will have this. If this was 0. And this looks familiar in form. Then you can compare this equation with the conservation of charge equation, which is of the form del rho by del t plus divergence of J. So that here, the energy density plays the role of the charge density, and the Poynting vector plays the role of the current density. So that's why I said there's a do with the flow of something. Okay, so this is the conservation law for the system, the whole system. The particles and the field. And I think I still have 10 minutes. I should at least start the discussion of the conservation of linear momentum. We will not be deriving the result for conservation of angular momentum because it's too complicated. Okay. And instead, we will talk about a very illustrative example, to discuss the conservation of angular momentum next time. But now let me start on the discussion for conservation of the linear momentum for this whole system. Okay, so let me go back here. So to discuss conservation of energy, I have to start with this discussion of the rate change of energy. To talk about conservation of momentum, of course, I have to talk about the rate change of momentum. But rate change of momentum is nothing but the force itself. So in fact, I have now got to start with the whole expression for the force in the Lorentz force law. And so now this is gone. E plus E equals B and QM. B, what is that? Oh, okay, sorry, this E. So I have to keep these two terms, these two complicated terms, unfortunately. All right, so let me go into the continuum discussion. Force, acting on the charged particles, inside a certain volume, is given by the volume of Q, of course, is rho E, and then this is nothing but current plus E, then plus, this is nothing but, rho M times B minus, also not mu naught, QMV goes into, the magnetic current. Again, most people will not put in these two terms, but I said, it's okay, I put in there for calculation purposes. After the calculation is done, I put rho M equals 0 instead of Jm. But of course, once I have put in the equation to get rid of rho and Jm, they are not there to start with. So this is accomplished with ease, and it's natural. All right? This, of course, is and then the transformation goes to this, and vice versa. This goes into that, and vice versa. All right? So now, I've used rho. Oh, wait. volume of the group of force density, small f. I think that's the notation Griffiths uses. So the F is this. So F is equal to rho E. I now use this equation to write rho in terms of the field. So this is nothing but, okay, let me get rid of all the minus signs. No, just not confuse myself. So this is epsilon naught E times divergence of E. Okay, that is this term. I can write down the analogous term here. So this would be, let me use green color for this term. So that is plus 1 over mu naught B times divergence of B. Rho m is times B. And you can check for yourself very easy that under direct transformation, this term goes with this term and vice versa. Next, more complicated things. I now want to get rid of write J in terms of the field. J is this. Now I want to write it. So this is plus J is curl of B divided by mu naught. Minus epsilon naught del E by del T. That's my J, and I have J equals B. It's getting more complicated. And then this term. So minus epsilon naught, mu naught. Okay, dm is here, okay? So this dm with a sign minus, so this is, oh, wait a minute. Oh, this is minus sign, minus, okay? So I may as well put this minus with j, so it's a minus dm, which is here, okay? So minus dm is nothing but, okay, plus Jm is plus this is curl of E over mu naught. And goes to the other side, becomes plus 1 over mu naught and del P by del T. That is my this term minus epsilon mu naught. Epsilon mu naught times minus Jm split is that, and those plus, right, and then I have mu times E. Okay, these two terms are put in, okay, just by hand. They refer to the magnetic terms. But if you are like other people, a lot of other people, you do not include these two terms, then these two terms will not be there. However, even when those two terms are not there, in the absence of the green sources, in the Maxwell's equation, you can still write these two terms in, because this itself is zero. Divergence B is zero. So you said, oh, what's wrong with put it in zero here? It turns out that this is the zero that I want. 0 times this is still 0. And this also is 0 in the absence of the green term. Why? Because this is still that, so that this plus that automatically is 0. So those people will say, I just put in 0 in this form here, and put in 0 in this form here. And you ask them, why are you so smart? He said, I know, because I want a term. Okay, this term looks like this term. And okay, open some kind of symmetry, name it duality symmetry. And this is that. And again, my answer is, why not put in by hand in the first place? So that you don't have to guess, you don't have to naturally list there. Now, once I've done it, okay, I can now put the sources, OM and JM in 0. The OM and JM are not in my expression, so it's fine. Okay, all right? So let's start the calculation, and it will take some time, and we will finish up the calculation next time. And we do not have use for it anymore. I hope I've not made a sign mistake or something. To start, let's take a look at the delta delta term. This here, this one, and this one. The del by delta term is minus del by delta t. This one is epsilon naught E equals B. With this del by delta it's on E. And then there's the del by delta acting on B, which should be this term, del B. But there's a minus sign, and there's a plus sign, that's okay, because I didn't change B and E. So that these two terms is just given by this. Next, let's take a look at the terms quadratic in E. Quadratic in E, this green color, this, and this. Cool. Okay, so let's see. What do I have? Okay, quadratic. These two terms. So then I have, okay, let me come it down first. Okay. Epsilon naught E times with E, and this term is, okay, mu naught cancels, so our still is epsilon naught of curl E bracket cos E. Have I done it right? Mu naught cancels, epsilon naught curl E, right. Okay, the important thing is to work this out. It's a triple cross product. It's complicated. Okay, there are two terms. Okay. Let me think of this. This gradient actually not on one of the e's, say this one, and not on this one. You have to remember this. So that there will be a term in this direction. So this on the other side is the minus, so the gradient. Now E dot E, since there are two of them, so I put in the first of 1/2 E squared. And then there's a term in the direction of E, and plus, who's the other side? Okay. This will be minus, but now, since this is plus, plus E dot squared dot E. Okay. So, and next time, I would combine this term with this term first, and then write the whole thing in a very nice form. So, we'll continue next time. So this is at the middle of our long calculation. All right? So see you next time.